Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist, what I'm calling Continuous Random Variables. Let's jump to today's topic, which is Continuous Uniform Distribution on an Interval. So let A and B be two given real numbers such that A is strictly less than B. Let X be a point in this set, any number between A and B, such that for any subinterval A, the probability that X is in A is proportional to that length of that subinterval. The distribution of the random variable X is called a uniform distribution on the interval A to B. Now, there's a tendency to define that all points between A and B are equally likely or have the same probability. But in continuous distributions, the probability of any given point is 0. So that's true for any continuous distribution. The probability of 2 points have the same probability for any distribution, right? Because it's 0. So you have to define it in these subintervals, and it's proportional to the length of that subinterval. And that's how you get to the definition of that uniform distribution. Let X be a random variable with a uniform distribution on the interval A to B, then the density of X is given by f of X is 1 over B minus A. Now these are two parameters, A and B, they have to be given. And we're going to prove that this is the density. So let the density be a constant value. Just call it C. And we know that if we integrate the density over its domain, we get 1. But let's let the density be some constant value. And then the antiderivative is X. Plug in, evaluate it in B and A, and we get this. Factor out of C, divide B minus A over, and we get 1 over B minus A. And that's what we wanted to show, what that's equal to the density. Let X be a random variable with a uniform distribution on the interval A to B. Then the mean of X is given by the expected value of X is A plus B over 2. So let's prove that. The expected value of X is you take X times its density, integrate it over all possible values. So X and the density is 1 over B minus A. Take the antiderivative, which is X squared over 2, and the B minus A was a constant. Evaluate it at B minus evaluated at A, and we get this. You can factor the numerator into this. We get cancelizations, and we get A plus B over 2, as we wanted to show. Let X be a random variable with uniform distribution on the interval A to B. The second moment of X is given by this quantity. Now let's prove that. The expected value of X squared is, of course, X squared times its density integrated over the domain, which is this. Take the antiderivative, get X cubed over 3. Let's evaluate it at B and A. We get this. The numerator can be factored into this, and then we get the B minus A's canceling, and then we get what's this fraction here, and that's what we wanted to show. Let X be a random variable with uniform distribution on the interval A to B, then the variance of X is given by B minus A squared over 12. The proof is this: the variance of X is using the computational formula for X is the respective value of X squared minus the mean squared. Well, plug in the two quantities that we derived, and then that simplifies to the variance. And so we're finished. I'm not going to simplify that. Let X be a random variable with a uniform distribution on the interval AB. Then the moment generating function of X is given by this equation. Oh, that should say mx of t, and I'll fix that in the hard copy, but it's wrong here. It should say, put that right there. So let's prove it. So mx of t is the expected value of e to the tx. So you integrate e to the tx times its density over the domain. Then the antiderivative is this. It's e to the tx divided by t, and the b minus a, of course, a constant. Evaluate it b and a, and we get this. Now, a big note here. Note that this is the form given in books, and so we're going to stop here. However, in its present form, it's not very useful, because when you plug in t equals 0, you get something that's undefined. So in another video, I'll devote the entire video on this topic, but it won't be part of this playlist. It'll be a separate part of this playlist, and it'll probably be a few months down the road when I get to it, but I promise. Let's do a quick example. Assume that when you press the elevator button, it takes between 30 seconds and 1 minute 15 seconds to open. Let x be your waiting time and assume that it's distributed uniformly over the interval. Find your mean wait time. So the answer is this. Well, this is a uniform distribution over an interval. So f of x, the density, is 1 over 75 minus 30. So the mean wait time is expected value of x, which is 30 plus 75 divided by 2, which is 52.5 seconds. Now, a quick R illustration. Let's integrate x times the density of that uniform distribution, and we're plugging in the values that we have up here. 30 to 75. We're integrating it over 30 to 75, and we get a mean of 52.5. And that's we better, because that's a theoretical. Now, what's the probability that you wait between 40 and 50 seconds? So we integrate the density, the uniform density, from 40 to 50, right? Because we want to know the probability being 40 to 50. Now, this min and max are actually arguments to this density function. So we're integrating it from 40 to 50, and we get 0.22 forever. Another way to do it in a uniform distribution is the difference of CDF functions, and that's P uniform. D uniform is density, P is the CDF. So we take 50, and our uniform goes from 30 to 75, and we're subtracting off P uniform 40, and the uniform goes from 30 to 75, and we get 0.22, as we should. Okay, let's see what the next video will be. It will be the gamma function, which is different from the gamma distribution. We're going to look at the gamma function first. Well, I hope you enjoyed this. We're right at 8 minutes. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.